Well, first of all, what are we really interested in when we evaluate a population? What do we want to know about a population that, when we evaluate it? Statistics. What's that? How spread out it is. That's one thing. And the other is where the middle is, right? So, for instance, if I were to, let's say I'm interested in comparing the blood pressures of in a population where some people have high cholesterol and some people have normal or low cholesterol, right? I want to compare those two. Let's say there's 100,000 people in that population that have high cholesterol, whatever way I define it, right? But there's 900,000 people that have normal or low cholesterol. Okay, and I want to compare the blood pressures of these two groups. Well, I got 100,000 people. It's not going to be very useful to look at it individual to individual because I'd have to, make 900,000 or more comparisons, right? 100,000 times 900,000 comparisons, all these individuals. So it's not very practical. So what we want to know is we want to know what the mean is, what the middle value, what the average value is for the people with high cholesterol and the middle value for people with low cholesterol, mean blood pressure for them and the mean blood pressure for this group. And if we know that, then we can start to deduce whether or not there's an association between blood pressure and cholesterol. That's really what we're doing is comparing things, right? But in order to do that comparison accurately, we need to know what the mean of these two populations is. And the mean of these two populations is mu, right? How often do we know mu? We almost never know what mu is. We're never going to know what mu is. In other words, if I take this population, I'm never going to go and measure the blood pressure of 100,000 people and 900,000 million people, right? That's just not going to happen. So this is something that we're never going to know for sure. That's what we want to know, but that's something we're never going to know. In order to also understand this, we're also going to want to know the standard deviation. Well, again, I got a problem with that. In order to know what the standard deviation of these two populations is, I would have to measure every person in that population and calculate a standard deviation. So either one of these two are things we're never going to know for sure. So the only option we have left is to sample the population. Okay, so now sampling is going to become an important thing for us. Okay, the first of the videos I'm going to show you is going to involve samples. Okay, but we know some basics about samples, right? We know basically that it's important that the populations that we sample are independent of each other. We also know that the samples should be random, right? Or won't be meaningless. In other words, if we went to a health club and measured people with high cholesterol, well, and we only measured people in that health club rather than all at 100,000, my expectation is there might not be the same average we get as we would get if we had sampled the entire population. It might be different, right, than people that didn't exercise in addition to having high cholesterol. So that might be a little tricky, but we need to make sure it's random. The sample is random. Okay, we also study design plays into this and so on and so forth. We're going to be getting into that. But the big thing that we're interested in right now is how are we going to estimate mu? Okay, and what am I going to do to actually know what mu is? And we know already we're never going to know for sure what it is. Well, I'm going to give you, since we don't know what mu, can never know exactly what mu is, it would be maybe at least we can understand if we take a sample from both of these populations of 100 people in each of these two populations, take the average of that sample. Let's say this one comes out to be 90 and this one comes out to be 84. Well, perhaps since I can't know for sure whether it's really 90 and really 84, since I'm going to call that X bar, the mean for people with high cholesterol, and X bar for the mean with people with normal cholesterol, right? Since I don't know for sure that 90 represents the true mean of that population, perhaps the second best thing I can understand about this is how far off I might be from 90. Okay. So, or how far off I might be from 84. In other words, understand how accurate or inaccurate that 90 is, right? Anybody have an idea of how we might guess at that? How might we guess if we take a sample of 100 people? How might we, and we found an average of 90, what tool might we use to determine how close to 90 the true population mean really is? Anybody want to hazard a guess on what we? I mean, imagine now you see all those bearded guys and that woman. She wasn't bearded, but she was a woman that I have on the banner for the class. Let's say you're one of those people, and it's 1823 or 1864 or something like that, and you're inventing this, right? So you take a sample of 100 people, you get an average of 90. Now, what could you deduce from that sample of 190 besides the average of 100 people, besides the average that might help you know how accurate that 90 really is? Standard deviation, exactly, right? You calculated this. I'm going to use SD because, in this case, we don't know the population standard deviation. Also, so if you look at your 100 people, if those 100 people have the range, the difference between the smallest value and the largest value is 70 to 140, right? Well, that's a pretty big range, right? So maybe 90 is not all that reliable. But if those 100 people had a range of, say, 85 to 95, well, gee, now you say to yourself, gee, it sounds like I have a pretty good handle on what the average blood pressure is for this population. That's what we're getting into now. This is real statistics. What we were talking about with knowing the population before was all based on kind of theory, what we understand about normal distribution, the formula that it's based on, and so on and so on. But this is really what you're going to be dealing with on a day-to-day basis. When you read a study, this is what they will be doing. They won't know what the mean is for group A or group B or group C, but they will be able to use the data that they collected to predict how well they know it. They get a number, but not so much know that it's the exact number, but at least be able to deduce how accurately they know that number, at least within some range of probability. So you guys have probably heard the term confidence interval. Anybody here not heard that term before? Right, you see on studies all the time, right? Confidence interval. Okay, what that means is that we want a range of numbers. In other words, we found that X bar is equal to 90. Well, what we would like to know is we would like to know what level of confidence that we have on that number. But we're going to know that by creating a range of numbers, a range, say 85 to 95 or 180 to 100 or 120, or 70 to 110. Okay. Which of those three ranges I just wrote up there would you have the most confidence that it contained the true mean? 85 to 90 is the least confident because it's so narrow, right? In other words, if I told you, with just knowing that the mean was 90, right? And I asked you, okay, without knowing anything else but what I told you the mean is, and I asked you, I want you to put $100. I want you to put your pay. We're going to put our paychecks down. We're going to bet our paychecks, right? Put the paychecks on the table, and I'm going to ask you which of these three ranges would you like to bet that contains the true population mean? Which one do you have the most confidence in? It's going to be between those two numbers. It's going to be the widest one, the biggest one, right? So you're going to bet your paycheck on that one, not on the narrowest one. So the highest level of confidence is the widest one. The lowest level of confidence is the narrowest. What's the number to the bottom? 10? I think it's, what did I write there? I wrote 70 to 110. Okay. 70 to 100. I just added numbers. Yeah, that was 80 to 100 and 85. It just made them wider and wider. Okay. So as that interval gets wider, now the only problem is that I just made those numbers up. What we really want to know is that what would you say in statistics? If you had to do studies and stuff like that, how confident would you like to be that you actually got the mean correct? Now, if you were to give me a range, how confident would you like to be that you actually got the within that range? You actually have the true mean. Would you be satisfied with 50% confident? Would you want to be 95% confident? Would you want to be 100% confident? You would like to be 100%, but you're never going to be 100% because the only way you be 100% is if you know what the population means. We don't know that, right? So we're not going to be satisfied with 50%, maybe 95%, maybe 99% would be even nicer. But I say to myself, it's going to be tougher and tougher to be 99% confident because just by reason, I say to myself, gee, in order to be more confident that I know what the mean and the standard deviation is, I have to have a bigger and bigger sample. So that means as you go up in confidence, it's going to get more and more expensive to do a study and more difficult to do a study, the higher level of confidence that you want. So for the most part, what you're going to hear most about is 90, 95, and 99% confidence. Okay. You want to be that's the level of confidence that we have that our conclusion is correct, that the mean is between these two numbers. And how are we gonna determine that level of confidence? Well, we know it's going to involve the standard deviation. Okay, we don't know the standard deviation, but we know that we can also estimate the standard deviation from the population, that 100 people that we sampled, just as we could calculate the mean. Okay, in the beginning now, as we work through this stuff, the I'm going to assume for the moment, just for now, that we know what the population standard deviation is. I'm doing that because rather than throw in two unknowns, I'm going to keep things simple by just talking about one unknown, just the mean. I'm going to make believe we know the population standard deviation, but we don't know the population mean. Now, that's not an impossible situation. I mean, somebody might have done a very large study with 80,000 people and gotten some data from the same population 40 years ago, and you pretty much think that you have the standard deviation, population and standard deviation pretty well nailed down, and you might want to assume that you know it, but you're taking a subsample from that population and you're looking for something else, and you want to take you want to assume that you know the standard deviation. It is possible you might be in a situation where you might do that. But for the most part, the only time you're going to know the standard deviation and not know the mean is when I tell you that you know the standard deviation for our first few exercises. Okay, so why do we want all this? Well, we want all this because this is really what we're going to be learning going forward. We're going to be determining a statistic. Now, that statistic could be, it could be something that compares the means, compares mu1 up to mu2. That's called a t-test. It could be something that compares multiple means. That's going to be called an analysis of variance. Don't worry about that name. It's very misleading. It could be a number. It could be something called a chi-square. But we're going to be taking samples, comparing the samples to each other. But in each case, we're going to be generating not the exact answer, but what our level of confidence that we got the right answer is. Right? So that's really what we're going to be doing. And this idea of doing these kinds of comparisons is basic to what we're going to be doing. So this is kind of a fundamental thing that we're learning here about where we're going forward with this stuff. Okay, so keep that in mind. So there's two things: fundamental. A lot of this is just like a mental exercise, just like we did before. But if you know what it is, it's going to be fun too. So it's fundamental. Okay. So at any rate, so we're going to go forward with this. Okay. So I'm going to start off. There's let me download this. I don't think I have it on my machine right now. Let me go into Blackboard and download these files. There's some files on Blackboard for the this class session. Okay.
Yeah.
And let's see. Let me get to him. By the way, I did try to get the stuff up a little earlier this week. I know some people like to be able to download the PowerPoints. I'm sorry. Print it where you use it. Use somebody else's toner cartridges for class. Yeah, I don't blame you. It's like a benefit, right? Let me just put this on my desktop so I have it. You guys might want to download these also to your desktop so we can work with it. Oh, that file name is taken. This is week 8. What are we in, week 7 or week 8? No, we're past that. It might be named week 6 because we have we took the exam, or so I'll call it week 7. Yeah, it's week 6 on here, but that doesn't count the exam. We're almost halfway through, believe it or not. Time flies, right? I'm going to be using all of these. So I'm going to download them all. Okay, let me get this out of the way.
We need to download all of the week 6 lab exercises.
Yeah, it wouldn't hurt. I mean, since you're doing it anyway, it's just a right click and a save anyway, once you're there. Okay, so now I am going to, where the hell did it go? Oh, here it is over here. It's hidden. Okay. So I'm going to open up this Excel file called population of 100. There we go. Okay, so what this file represents, this file behind me represents a normal distribution. Okay, in Excel, you can actually tell Excel to produce a string of numbers that are normally distributed with a certain mean and a certain standard deviation. There's a function that in Excel, I'm not going to look it up right now, but there is a function in it that'll help you create numbers like that. So presumably, I don't know how accurate. Suppose we could throw these numbers into SPSS and create a histogram and see how truly normal it is. But I'm not worried about that right now. We're going to assume that it's a normal distribution. Okay, so this is the entire population. Now, in real life, you're going to be dealing with much larger populations, right? You might have a population of 100,000 people, 1 million people, everybody in the United States, population of all the people that have diabetes, population of all the people that are Bronx that have gone to emergency services in the past 12 months, et cetera, et cetera. You're going to be usually dealing with very large populations, not 100 people, right? 100 people, you could just sample everybody and just find the mean for everybody. No need to have statistics, right? No need to be able to deduce this stuff. But we're going to make believe that this is a large population, this 100 people, and too large a population for us to sample. But it's going to be manageable for us to work with here. So I'm going to find the mean. I'm going to type mean here so we know what I got of this population. This is mu, right? Oops. Okay, the average of all these numbers. The outside numbers are just identifiers, just like the ones in Excel. Okay, the mean is about 50. Now I'm going to put u over there, and this is sigma. Okay, a standard deviation. Okay, and I'm going to calculate standard deviation for this whole group. And standard deviation for this whole group turns out to be about 9. So if I wanted to take a wild guess at, if I were to ask you, what percentage of these 100 people is between 30, 32 and 68? What would you tell me? What percentage of people in this population of 100 people are between 32 and 68? Well, that's twice 9, right? What is 9 standard deviations? So that's 2 standard deviations below the mean, 2 standard deviations above the mean. So what percentage of the population would you expect to be between those two z-scores? 95%, right? It's a normally distributed population, 95%. So that means 5 people would be lower than that number, and or higher than that number total, right? 2 or 3 lower, maybe 2 or 3 higher. Okay, just basically just a normal distribution. We're making believe that this is a population, and we know the whole population. Okay, so this population has a mean of 50 and a standard deviation of 9, sigma, population standard deviation. So now, we as statistician now, we're going to look at this population. We don't know any of these numbers. As far as we're concerned, all of these squares here are all blank. We can't see them. When I was in junior high school, I got shut out of a wood shop, because they filled up the class or something like that. So they forced me to take typing. This is like, literally, they forced me to take typing. This had to be junior high school. God, this is in the early 60s we're talking about now, right? They forced me to take typing. I wanted to shoot myself. I didn't want to go take typing. I wasn't interested in typing. And they put us in a room with these giant mechanical typewriters with no letters on the keys. And they taught us to touch type, right? That's got to be most valuable skills going forward. And I'm sure they had no idea how important it would be in the future. But like 40 years, 30 years ago, when computers started to show up, you know how many of my colleagues couldn't type? Right? Hunt and peck. Now everybody types because they type instead of writing now. Right? Exactly. Now you're hard pressed to find a school that teaches script anymore, right? So at any rate, so let's imagine that that's those keys, right? They're all blank. They're all like, what's that game where they cover them up and remove them and stuff like that? Yeah, it's a memory game. There's things behind it. You flip it up. Concentration, I think it's called, right? Or something like that. Imagine it's those, and the tiles are all covered up. What you're going to do now is we're going to all sample this population. Okay, so let's see, we've got 100 people. I'm going to say let's take a sample size of 9 people from this population. Okay, so I'm going to ask you guys to randomly choose 9 people from this population, right? And the way you're going to identify which ones they are is just like an Excel spreadsheet, like column, like row 2, column 4 would be 45. Row 5, column 6 would be 46, right? Okay, so I'm going to ask each one of you to randomly select 9 people, write it down, and then you're going to calculate the average for those 9 people. But before you do that, I'm going to ask you, how are you going to do a random selection? Hunt and peck. I mean, if you're left-handed, you're going to get different. You're going to tend to, if you're right-handed, that's not random, right? Your eye might catch certain numbers rather than other numbers, just because they're numbers you're familiar with, your birthday, something like that, right? So you can't depend on yourself to do a random selection. So you have to have a mechanism for doing that. Well, there's many mechanisms. Some of them are computer generated and so on and so forth. On here, I gave you something. I'm not sure there's one in the. This is from a different textbook than ours. I'm not sure there is one in ours. Open. Let me just take a look. Open intro. Open intro. Is there a random number table in there? I'll do a search. Random number. See if there's something in the back. Tables. No, I don't see it. How about in the index? There's none of that. No, there's no random number table in here. Okay, this came from a different book. This is a table of numbers. It's on black. It's on, actually get kind of an introduction to it here too. You can go to any page here that you want. There's a bunch of pages here, right? You go to any page that you want. Somehow or other, they generated these random digits, right? 0 to 9 digits. How did they do that? Any number of mechanisms. They could have a computer program do it. A little bit funny, kind of thinking that something that's a programmed device, like a computer generating random numbers. But there's ways that they can do that. They can also do it based on the generation of random natural events. Like one of the things that they do is the time that it takes for different radioactive elements to decay and release particles. That's kind of there's a randomness to that effect. So they can actually use that with scintillation counters and stuff like that to generate random numbers. But this table somehow or other they might tell you how they did it, but even if they didn't, the idea here is I can go to anywhere in this point, and I'm going to start right here. Right? I'm going to start right there. So the first number that I see here is a 5, starting there. You can start anywhere you want because from that point on, it's always going to be random numbers. Okay, but now I'm not relying on myself to generate a random number table. I'm relying on another device that's already been randomized. Okay, so I've taken that control away from myself. It's kind of like you do double-blind studies. The person that gives the person the injection or the drug doesn't know whether they're giving them the drug or the placebo. Protects us from influencing the study. So I'm going to start with a 5. Well, actually, what I need is I really need 2 digits. I need a column and a row number to randomly select something. So my first column and row number is 58. Row 5, number 8. Row 5, number 8 is going to be the number 66. So I'm going to put that over here, 66. So you guys do exactly, and then I'm going to go back and take the next 2 numbers, 96. And then you got a choice. You can go across. I would probably go 35 and 22 and 20 and 76 and so on. Okay, you can do it any way you want, but just just follow a sequence. Don't jump around the page because then you're doing the same thing you would otherwise. Okay. I'm looking at the randomnumbertable.pdf.
So, go again, Professor. How we choosing? How we choosing again?
Just start anywhere. Pick 2 numbers like this is 81, right? So that would be row 8, column 1. Row 8, column 1 is 63. The next one would be 49. That would be 49 would be row 4, column 9, whatever that is, right? So pick out 9 numbers. I'm going to do it myself. I'm going to go back to where I was, if I can ever find it again. You can look over on somebody else's. I'm going to give you if you did something in the medieval times, you did something really nasty, right? And you didn't want to go to hell, you could go pay the Pope, and the Pope would give you a papal dispensation, right? So I'm going to give you a papal dispensation. If you want, you can just pick out randomly since you don't have the table. Right?
Oh, it keeps saying before proceeding, you must first launch Adobe.
Yeah, Adobe Acrobat. It's not opening on yours. It may not be installed on that machine, maybe. Yeah, you don't have to worry about it. You can go ahead and just pick them out.
You go to random.org.
Oh yeah, there's also you go online. There's random tables on, and random number generators online if you want. Random.org.
We had to pick
9 numbers, yes. Randomly pick 9 numbers. Yeah, I'm falling behind you guys here. I'm gonna start from this. I'm gonna go back and start somewhere else now. I gotta make this smaller. Don't worry about it. We're never going to do this again. So it's not like this. This is not going to be a valuable skill going forward. Okay. So, but I'm really trying to demonstrate something else here rather than, how to calculate random number, how to determine random. Well, that's a skill also that might come in handy in the future. Maybe I shouldn't say that. Maybe it is a handy skill. So 66. Okay, 76. Row. I'm having a hard time doing this because I can't see the random number table and this thing at the same time. I'm going to temporarily make this smaller.
Wait, how many numbers do we have to pick?
9. 82. I'll start from here. 82. 49. 58. I think I just picked 58. Yeah, that's okay. 71. 40. 71. 40. Where was I here? Keep losing my place. 35. is that one? 8, 9, and 9, 8. 8, 9, 7, and 9, 8, 7. I keep losing that. There we got 18 and 28. 1 is 61. 11, 12, and 15. 15. Oops, that's not quite what I need.
Got it?
Go to line. You're picking out 9 numbers randomly from that table and finding the average.
When you say how is this paper associated?
What's that?
How is this paper?
Yeah, well, that's how you're determining which 9 numbers that you're going to sample randomly, right? You're gonna, in other words, if you start at any point in that table and look at the first 2 numbers you see, use that as the row number and the column number for the first number. And then take the next 2 numbers, use that as the row number and the column number for the next number. So do that 9 times, and you'll find out what an average. Now I'm going to tell you guys, you can round it to the nearest whole number. Like, I got 49.67, I'm going to call it 49. Okay, I'm only going to do that because I'm going to ask you guys to yell up to me in a moment what numbers you got, and I don't want you yelling up 49.773473. You have to type it. I'll go over here, put this over here.
Just choose 9 random numbers.
Okay, so as you guys finish that, yell up what number you got. 48, and I heard a 47 there. Oops. Hang on a second. 51. How much? 50. Next. 46. Good. Next. 54. Okay. Did I miss one?
I'm just gonna say someone online said 55.
Okay, 55. Thank you from the peanut gallery there. Nadira, thank you.
Minus 50.
I don't think you got minus 50.
Oh, 50.
50, okay. Okay. I'll wait for a few more. I don't need a million of these, but.
So I'm just gonna say this for population of 100. So can we say that each box represents one person and
Yeah.
you're assigned a number, almost like a jersey number on a sports team?
Yeah, exactly. And you were actually like a social security number,
Okay.
right? So one of the ways that you might do a random selection of people from a population is you might if you have an ID number for them, like a social security number, you might ask the computer to randomly select people from their social security number, and then that person gets called up and surveyed.
It's just
Same
weird
thing,
how-
random. Also, when you do a phone survey, you might, if you're interested in the Brooklyn, you might have a list of all the numbers in Brooklyn, and then randomly select phone numbers. So you don't know the person ahead of time. But yeah, in this case, we're just using like a device to decide how to out of these 100 people, how to randomly pick 9 out of that 100 people.
It's strange there are no numbers in like the teens or the 80s.
Oh yeah, but well, you know why? It's not strange, is it? Because it's a normally distributed population.
Uh-huh.
So the we would expect 95% of the population to be, if the mean is 50 for the whole population, 95% to be between 18 below that and 18 above that, which is 32 to a 68, right? And if I went even to, if I went another standard deviation below and above, right, I'd expect almost 99.97%, basically everybody within three standard deviations below and above. That's why you're not seeing any hundreds and any 12s or anything like that, because that would be a very unlikely outcome for a population that has a mean of 50 and a standard deviation of 9. Okay, anybody else? 49, okay, good. Anybody else? 51? Okay, I think I got enough for now. Okay, so now we have taken 5, 6, 7, we have 10 samples of size 9, right? Normally in real life we'd only do one sample, right? But we have 10 samples. So what I want to know now is, gee, what's the range on these 9 people, on these 10 samples, the averages that I got? Well, the lowest was 46. The highest was 54 out of the 10 samples that I took. What about the population? Well, look, I see a 32 in here, and I see a 69 in here. The spread in the population is much wider than the spread of samples of a particular size. Should that be a surprise? Not really, right? Because you would never expect to get if 69 happens to be the highest value in here, if I were going to take a sample of 9 people and average them, I wouldn't expect to randomly pick 9 people that are 69, right? That would be a rare event for me if the highest, it would be very rare for me to pick all 9 people out of a population that are the most weight or highest BMI by just picking randomly. That's a very rare event. That probably would never happen. Okay, so when we take a sample, the average, the means of those repeated samples is going to be a narrower range than the actual population values. Right? So if this is blood pressure and it's not going to be blood pressure at 50, but if this is blood sugar or something like that, the average blood sugars that I take for each sample is going to be narrower than the range of blood pressures in the population. What do you think is going to happen the bigger the sample is? The more likely that your average for each individual sample is close to the mean. So the spread for your repeated samples is going to be narrower and narrower and narrower depending on how big a sample that you took. Yes?
So another way to say it is the more samples you have, the smaller the standard deviation.
Well, no, actually, no. The number of samples that you take are not going to affect it.
Yeah.
It's really how big the sample size is going to affect it. Because if we repeated this for another 10 people, we probably would get a pretty similar result. So the spread's not changing, right? But I'll bet you that we'll get a better idea because the spread's not changing if we did exactly the same thing for another 10 people. However, I told you take a sample of size 25. Now all of these numbers would probably be closer to 50, right? And if we did it twice, it would be closer to 50 again. So it's really the sample size that determines the spread. So let's see what we got here. Let's see what the average is of all these samples. Now remember, this is the average, the mean of repeated samples. Okay, and the average comes out to be 50. Actually, it's not really 50. We know it's really fractionally bigger than that. Let me just make sure that we have that. Okay. Oops. It's really 50.3, which is pretty close to what we have. 50.14, it's pretty close, right? So now that's pretty close to the actual mean. That's what we expect. When you take an average, you do it over and over again, we would expect to get pretty close to the actual mean. Let's see what happens to the standard deviation. What's the standard deviation for the repeated samples? It's 2.69. What was the standard deviation for the population? 9, right? So it's about a third of what the population standard deviation was, right? So I kind of gave you a little bit of a key there. It's a third of what the population standard deviation, say 3 to 9, roughly, okay? So what's the relationship between 3 and 9? One's the square root of the other, right? So we just discovered a very interesting property of samples. Where'd my notepad go? See if I can't find it again. It disappeared. I'll have to pull it up. we just discovered a very interesting property going on here. Okay, we got the mean here, we got the standard deviation. We started with a mean of 50, standard deviation of 9. We took repeated samples of size 9, and we got a mean of 50.4. But we got a standard deviation, this is x bar, oops, x bar, and we got a standard deviation of about 3. So what happened here? Our mean, our samples did a pretty good job of approximating the mean, right? Approximating the mean. But now our standard deviation of our repeated samples now is the square root of what the original was. So our standard deviation for our samples is going to be equal to our standard deviation of our population divided by the square root of the sample size. Now, this is not a real derivation of this relationship, but you can see the demonstration of it here. This standard deviation represents if I have this population and I take sample after sample after sample of the same size 9, take repeated samples from this thing and make a new distribution. That new distribution is going to be narrower, right? Because the sample means are going to be narrower, but it's going to have the same mean. Both means are going to be 50, approximately 50. But my samples, repeated samples, well, the spread is going to be dependent on the sample size. And it'll be the original standard deviation divided by the square root of how many people I'm sampling, the sample size. We're going to give that spread, that name, the standard deviation for the samples of the same repeated size. We're going to give that a special name. We're going to call that SE instead of SD. We're going to call that the standard error. Okay, that is something that we just learned now about how samples are distributed. Okay. First time out, don't get panicky if you can't wrap your head around this completely. However, the important thing here, right now, in order to solve problems going forward, is that when you take a sample, let's say I have a population, okay, and again, population, we don't know what the mean is, but we want to estimate it, okay. Let's say I know the standard deviation is equal to 10, okay, and I take a sample. I take repeated. If I take and the sample size I want to work with is 25. If I sample from that population over and over and over and over again, my average for all of those times that I sample it, when I take those, each time I took 25 people, found an average, 25 people found an average, my sample population is going to be approximately the same as the mean is. I don't know for sure if I catch it exactly. It's going to be, but if I do an infinite number of samples, it's going to be the same as the mean. Because an infinite number of samples is really going to be just like having the mean, calculating it for everybody. Because you will have sampled the entire population, right? But the standard deviation is going to be narrower. All of those repeated samples are going to have a smaller spread than the original population. So if the sample size is 10, my standard error, my standard distribution for the samples is going to be equal to 10 over the square root of 25, which is 5. It's going to be equal to 2. So 95% of my samples of size 25 are going to be between 4 below and 4 above, right? 2 standard deviations above what X bar is. Okay. So why am I interested in that anyway? What possible value could that have for me? Okay, well, the way this is going to work now going forward, and I just want to introduce it to you so you can see the direction we're going. Turn your mind off for a moment. Okay, don't worry about understanding this for right now, but I just want to show you the direction that we're going. So if I sample if I have a population, right, 8 million people in New York City, and I want to know what the average, I don't know, give me a physical characteristic of people in New York City that you think might be normally distributed. Not age, right? Because age is not necessarily normally distributed. How about blood pressure? Okay, average blood pressure. Okay, um, for 8 million people, some are going to be very low, some are going to be very high, but there's going to be some sort of average. So mu, I'm interested in that, but I can't find mu because I would have to slip a blood pressure cuff on 8 million people. It ain't going to happen. So I'm going to randomly select 100 people from those 8 million, whatever way I do it, right? I'm going to randomly select 1 million people. Now I take those 100 people and I find the average blood pressure for those for those 100 people, and the average turns out to be 81. Now let's say I told you that in a previous study they sampled many people in New Jersey, and they found that the standard deviation for blood pressure in a population similar age, size, ethnicity, and stuff like that was maybe 10. Okay, that's for a population. Notice I use sigma. Well, if I took repeated samples of size 100, right, I would expect X bar to approximate mu, right? So, but I might not get it right on the first time I took this sample. It might be close to it, might be far away. I'll never know for sure because I'll never know what mu is. However, I could say to myself, well, if I took samples over and over again and got a mean of 81, okay, and I know that the standard deviation for the population is 10, if I took if I took samples of size 100 over and over again, well, maybe I'd get 80, sometimes 84, sometimes 81, and so on and so forth. What would be the spread of all these samples? Well, I'm going to take that sigma. The spread of all those samples is going to be my standard error, which is sigma over the square root of n, which is 10 over 100, which is equal to 1. I would expect 95%. If I knew what mu was, I would expect 95% of the possible sample outcomes I would get to be between two standard deviations below and two standard deviations above, which is just 2 times 1, right? So I would expect my samples, if I knew what mu was and I took a sample of that size, I would expect that 95% of the time they would be within an interval of two below and 2 above, or plus or minus 2. So if I think if my sample mean comes up to be 81, I might be able to deduce and say, well, I found X bar. I found X bar is equal to 81. I may not know what mu really is, but based on the nature of samples and based on the standard deviation of this population, which I know, I can assume that I have 95% chance that the true mean will be between 79 and 83. That's called a confidence interval. I may not know what the real mean is, but I can say it's within 2 standard deviations and above the value that I had. And the standard deviation that you're using is really the standard error, which is based on the standard deviation of the population and the sample size. So that's called my confidence interval. That's almost as good as knowing the mean. Yes. Because when I take samples from a population and I draw them on it, they're all going to be normally distributed also. Two, two standard deviations above and below. Okay. In other words, 95% is normally the level of confidence in statistical studies that you find acceptable. Okay. You also might have seen somebody mention alpha error, like alpha is equal to 0.05. That's basically saying that I'm willing to accept up to a 5% chance of being wrong. Right? That's called alpha error. Okay, so a 95% confidence interval is kind of like saying the same thing. I'm 95% sure the true mean is between these two numbers, which means that I'm willing to accept 5% chance that it's outside of those two numbers. I'm sorry, say it again? Yeah, the question was, is it because it's a normal distribution? The answer is yes. Ideally, this works best with a normal distribution. Okay, so now I'm going to tell you, now that I've said that, I'm going to make myself a liar. Okay? And the reason why I'm going to make, okay, so now let's say you have a distribution that's not perfectly normal, that's maybe skewed a bit, like something like this, right? Because the process of sampling is a random event. You randomly pick people out of here. The chances that you'd pick somebody out from over here are lower than the chances you'd pick somebody out from over here. So what winds up happening is that you could start with a skewed or slightly skewed normal distribution for the population and wind up with a normal distribution for your sample distribution. Okay. All of this put together, this idea of that the original distribution doesn't have to be perfectly normal, and that the sample distribution, the relationship between the standard, the spread of the original population and the sample distribution, that sigma versus the standard error is the square root, the dividing by the square root of the sample size. All of that put together is called the central limit theorem. Okay, that's where we are now. Okay, we took a big leap here, right? We kind of like went from 0 to 100 real quick. So now we're going to go back and we're going to listen to a lecture, okay, about sampling and a few other things. It's going to be broken up into 4 parts. Okay, we're going to listen to it, pause afterwards after each one of them, and then we'll discuss it and move on to the next one. And then we're going to do some exercises where we apply the relationship that we just learned. Okay, and why is that important? Because now we have a mechanism where we can sample a population and understand how accurately we actually know what the mean for that population is. We may not know what the absolute perfect value for the mean is, but at least we know how well we know what the mean is. Okay, so let's give that a try. Let me do it on here. It can be easier. I think I need to escape here. Yeah. Okay, that's interesting. Look. Okay, minimize this. Go to I usually like to use the Hunter website because it's easier to get the black. They stick it right up there. Their public health site. They bury it or something. They have a lot of pretty pictures on there. They bury the important stuff. Would you like to make I think I thought I already answered that question. Would you like to store your password? So here we go. Okay. Now I usually put up a description of who these people are. I don't think I put it into. I usually put in course information. I got to check something like that. I don't think I do.
Yeah.
Did I? Is it in there?
No.
No, it's not. I have to put that up there. Okay. Okay. Sampling strategies. This is Lee. You guys know Levi Waldron? Any of you people ever bumped into?
We're calling this example of state of Massachusetts infographic for that.
Okay.
Population can be statewide population, countrywide, subsets of it, as long as it is a well-defined population for which we can enumerate who is a part of it and what.
I want to be able to expand it, so I think I got
parameters involved in being part of that population.
I'll turn it up.
Samples are randomly selected.
Okay, for you guys online, you might want to go on to Blackboard and run those 4 videos yourself. We're going to stop and discuss them in here. So I'm going to stop recording this part because it'll be easier to watch it on Blackboard. Come back when we're done, maybe about 45 minutes or so. Okay, good. There we go. Let me get this stuff out of here. Move this out of the way, and I'm going to open up another document in here called Introduction to Sample Distributions and the Central Limit Theorem. Okay, and there's that first exercise that we just did. So this is second to load, second scroll. Okay, so the first example here is going to give us just a rework of what we've been working on so far. This idea of samples and population. Okay, so we sample 100 bottles of detergent and find that on the average, each bottle, it's a good public health example, not really, but we'll start with this. Sample 100 bottles of detergent, sample size is 100. So immediately we know we're dealing with what, a population or a sample? Sample, right? Okay, so 100 bottles of detergent, find that on average, each bottle will be sufficient for 57 washing loads. You know that the standard deviation for the entire production line of 100,000 bottles is 5 loads per bottle. So I know my sample mean, right? And I know my population standard deviation. Unusual thing to know, right? Population standard deviation. But we're going to go with that assumption for now, just so that we can work out some exercises without getting into something a bit more complicated.
You're not seeing me right on the
Oh, no. Let's see. Why not? Oh, you're right. I haven't written anything, by the way, yet. I'm just reading from that document. Okay. There it is. Oops. I don't need this anymore. Okay. Let me blow that up a bit. Make it even bigger. Okay, so we sample. So let's see what we have here. What do we know here? We know our sample. We know our size of our sample is 100 bottles, right? So I'm going to put down here N is equal to 100 bottles. Okay, I know. Minute I know that, I know we're dealing with a sample. Okay, our average for our sample is 57. That's going to be X bar, not mu, but X bar. Now, our standard deviation for our sample, well, we don't need to know that because we've been giving the standard deviation for all of the 100,000 bottles. The whole population is 5 loads per bottle. So that is sigma, is 5. Okay, so let's go back and look at this problem. Is 57 mu or X bar? I kind of gave that away already, right? What is it? X bar, exactly. It's a statistic, not a parameter. Is 5 sigma or SD? Sigma, right? It's a parameter, not a statistic in this case. Okay, because it's been told to us. We didn't calculate that. Calculate the standard error for repeated samples from this population of size 100. Okay, what would the standard error be equal to? How do we calculate standard error again? Standard error is equal to, what's that?
Sigma divided by
Square root of n. So that sigma is 5 divided by the square root of 100 is equal to 0.5. Our standard error is equal to 0.5. Okay, so now calculate the 95% confidence interval for the population mean based on this sample. Well, how am I going to do that? Well, let me just draw what this should look like if we knew what the population mean was. If we knew what the population mean was, and I took samples of size 100 over and over and over again, what it would look like is something like this. The mean would be whatever mu is. I'm not even going to put a value down for it, right? And if I kept taking samples of size 100, right? Sometimes I would get 57s, hit it right on the head. So, assuming that's what it is, 56, 61. I would get all different values for the average of size 100. But I know that 95% of the time, the results of those means of size one of the samples of size 100 would be between 1.96 standard deviation to, right, if I use empirical formula, below the mean, and 1.96 standard deviations above the mean, right? Plus one, okay, C is, or two, plus two above the mean. Okay, so now the only problem is that we're not talking about the individual number of loads of laundry you get from each bottle, but of the repeated samples of 100. So this standard deviation that we're talking about is not sigma, it's my standard error, right? My standard error now represents the distribution spread for these repeated samples. So I would expect that 95% of the samples that I would take are going to be between, I'm just going to use 2 instead of 1.96 for the moment. I would expect that 95% of the samples are going to be between 2 times 0.5 or 1 below Z, 1 less than Z, or 1 more than Z, or Z minus 1, excuse me, mu, or mu minus 1, or mu plus 1. Going to be 2 standard deviations below the mean or 2 standard deviations above the mean. In this case, what's my standard error? It's 0.5. So that's going to actually be a 1 or something like that. Let's for a moment.
So you put in the 0.5. The 1 was just showing us.
I'll redo the formula so that it'll make sense to you in a second. Let's say for a moment that I'm going to assume for a moment that I got it right, that my true population mean is 57. Right? Well, in that case, I would expect that 95% of the possible outcomes that I would get for a sample from this distribution, when I take a sample of size 100, is going to be 2 times 1, 2 times 0.5 below, or 2 times 0.5 above, or 56 to 58. So my interval that I would expect to get repeated samples to spread out between 90%, 5% of the time, I would expect them between 56 and 58. Is that all the same? No, sometimes 2.5% of the time I'd get lower results. 2.5% of the time I get higher results. So let me extend this to the next step further. Yes?
Where are you getting the 2? Like, why is it 2?
2 standard deviations, because it's a normal distribution. So 2 standard deviations below to 2 standard deviations above is going to represent 95% of the population, or 90, in the case of standard error, 95% of the possible sample needs.
So
So
you
that,
multiply the 2 by the 0.5. You rounded the 1.96.
yeah, to 2. Yeah, but it's really 1.96. And from now on, I'm not going to round it anymore. I'm going to use 1.96. But now you know where it came from. Okay, so let me do this right now. Let's assume for a moment that I got this right, that X bar is, what did I say was 57? Sigma was equal to 5. My sample size was equal to 100. And my standard error is equal to 5 divided by the square root of 100, which is 5 divided by 10, which is 0.5, 0.5. Okay, so now if I take this distribution, I say to myself, well, for the moment, let's say I got 57. Where would I expect this range of samples to fall? Well, I would expect it to be 1.96 standard deviations below that and 1.96 standard deviations above that, right? Well, let's calculate that range.
Where'd you get 1.96?
The number of standard deviations below and above. We've been calling it two, right? Two standard deviations above to two standard deviations below represent 95% of the possible outcomes for what you would expect the sample mean to be. Yes.
I'm using the table A, B table, and I see 95% as 1.65.
That's because, remember, you're only looking at from that value down. So you're looking at 5% representing the lower tail. If you add the higher tail to it, now you're really looking at 90%, right? That's in the middle. But if you look at 2.5%, you're going to see 2.5% on the lower end, 2.5% on the higher end. That's going to come out to almost perfectly 2.250, right? To come out that way. Okay. So now, what I'm going to do now is basically the way you're going to apply this formula. Okay. I'm going to calculate my confidence interval. My confidence interval is going to be X bar plus or minus 1.96. I'm going to take X bar, whatever it comes out to for my sample, and add 1.96 standard errors to that X bar. In this case, the standard error is equal to 0.05. So X bar is 57 plus or minus 1.96 times 0.5. Okay, let's see what that comes out to. Okay, 1.96 times 0.5 is equal to 0.98. Okay, so I'm just going to take 57. Let me just finish this up. 57 plus or minus 0.98. So that gives us on the low end, it's going to be 56.02 to 57.98. That's the range within which I would expect there's 95% chance that the true mean is going to wind up within. I subtracted, see, plus or minus. First, I took 57 minus 0.98, leaves 56.02, and 57 plus 0.098. So my confidence interval in this case is 56.02 to 57.98. Okay, so are you guys confident that you could repeat that?
No.
No? Okay, let's give it another try then. Okay, I got a feeling the next problem is going to do pretty much the same thing. Suppose we want to know what the true population proportion. No, let's not do that one yet. That's another one. I don't like that one too. Let's see. For some reason I'm stuck on these washing machines here. Suppose we want to know the true population. No, I don't want. Like I said, I don't want. High efficiency washing machines use less water and less detergent. How many loads? Okay, some people want to do that. How many loads does a full 150-ounce bottle leading laundry detergent handle on the average? The results of the number of loads washed below represent 10 randomly selected users. So we have 10 people here that. Did I give you a? I'm looking to see if I gave you. I don't like this. I don't like. I'm jumping ahead to T-scores here, and I don't like that. I'm going to give you a different example. I'll make one up. Oops. Let me close this and reopen it. Okay. Okay, we randomly select 49 people from a population. We find that the average blood pressure for those 49 people selected from that population is equal to 92. We know from a previous study that the standard deviation for everybody's blood pressure in that population is equal to 14. That's the spread for the entire population. Okay, this is my sample result from my sample. So now I want to know what's my confidence interval for the true population that this sample came from. Okay, so how am I going to calculate my confidence interval? What do I start with? X bar, right? Plus or minus. So if I want a 95% confidence interval, what do I put here? 1.96, two standard deviations, right? Times the standard error. I don't know my standard error yet, do I? Right? What's my standard error equal to? Sigma for the population divided by the square root of the sample size, which is 14 over 4. Square root of 49 is 7, right? Okay, that's equal to 2. So X bar is 92 plus or minus 1.96 times 2, the standard error. Okay, so that's 92 plus or minus 3.92. I read about that? Yes, 3.92, correct? Yes. Okay, so what is my confidence interval? It's going to be 88.08, right? Just subtract 3.92 and add it, 95.92. That's my 95% confidence interval. We kind of did we did a little bit of a twist here. We're assuming that our mean is 92 to calculate this confidence interval. We're kind of twisting the real way that this works around to our advantage. Really, in real life, the confidence interval means that if you were, let's say I was going to display these blood pressures. Let me undo that. Get it a little bit better. Let's say that I were going to display all of these individual values for the actual mean, the mean of a sample. Let's say I knew that the real true blood pressure for the average blood pressure for the population was 100. If I took 100 samples from this population, right, and I would expect, and it turns out that my confidence interval was 110 to 90. That this was what my confidence interval was. I would expect that when I take 100 samples, 95 times it would be within these two ranges for 90 of 110, right? Maybe sometimes high, so okay. But 5% of the times, 5 times out of 100, it would be either lower or higher than that range. I would miss it with my sample. So when I tell you my confidence interval on the previous problem, I tell you my confidence interval is 88.08 to 95.92. I'm saying I'm 95% sure the true mean is between these two numbers. In a study, in the abstract, right at the beginning, they may tell you the average blood pressure was equal to 92 for this sample. Sample size was 49, and the confidence interval, 95% confidence interval of 88 to 96, let's say, right? They might give you that information right up front. They're not telling you that they know the true mean. They're telling you that we based on the sample size that we have and the variability of the data, we believe that our sample result, our average came up to be 92, and we believe that with 95% certainty we can say it's between 88 and 92. Well, why is that valuable? Let's say somebody did a study last year of the same population before an intervention, before they were trained on better eating habits and so on and so forth. And that study showed that the result they got was a blood pressure of 100 with a confidence interval of 95 to 105. Well, we may not know that 92 was right this year and 100 was right last year, but we're 95% sure that that the true mean last year and the true mean this year are different, right? Because they don't overlap. These confidence intervals don't overlap. Or if I'm comparing it to a known number, let's say I know that population B has a blood pressure of average blood pressure of 86. They sampled everybody in the population. I know now that I'm 95% sure that my population mean is different than that population. On the other hand, if our confidence interval had been 85 to 105, I couldn't say we're at 95% sure that that other population was really different. Okay, that's how we're using confidence intervals. Just to introduce you to the idea of this idea of proportions. Okay, we're not now that should be enough for you. There's one question on the homework assignment 4, which is I think do at the end of the week or something like that. There's one question. The last two questions, last one question on assignment 4 asks you to calculate a confidence interval. You have the tools right now to answer that question. Okay, but just to show you that we can do the same thing for a proportion. Let's say that I polled 100 people, and I asked those 100 people, how many of you are voting for Hillary Clinton in the election? And 52 of those 100 people told me that they were voting for Hillary Clinton. So what's the probability any individual in this population is voting for Hillary Clinton? Well, the probability we don't know, just like we don't know the mean. Okay, we're never going to know it unless we ask everybody in the population. In other words, unless you have an election, they actually do it, right? We don't know what the probability is, but I do know what the proportion is for this population. That proportion is 0.52. 52% of the people in this sample said that they were going to vote for Hillary Clinton. Well, you want to know something? We can do the same thing for proportions as we do for means, right? Notice that we did a little trick here. P was the proportion of the population. P cap, just like X bar, P cap represents the proportion of the sample, right? So now I need to know a standard error. Well, with proportions, the way we calculate a standard error, we say the standard error is equal to the square root of P cap, whatever it happened to be, times P times 1 minus P over N, the sample size. Okay, that's how we calculate standard. So we don't know. Ideally, we would like to use P, the actual population proportion, to calculate standard error, but we never know that. So we're forced to use P cap instead of P. So what would that come out to be? Standard error comes out to be the square root of 0.52 times 0.48 over 100. Okay, and what does that come out to? Let's see. 0.52 times 0.48 divided by 100 equals that. Now I got to find the square root of that, right? Square root. Where is it? Square root. Square root is 0.05. I'm going to call it. I'm going to round it off. So my standard error is 0.05. Standard error is equal to 0.05. So now, just like before, I know that my sample came out to 0.52. What is my confidence interval now for that proportion? So it's going to be P cap plus or minus for 95% confidence interval. What is it going to be? 1.96 times my standard error, which came out to be 0.05. I'm going to round this off to 2. So it's going to be to 2 times 0.05 is 0.1. So my one, I'm going to call this 2 times 0.05, right? Which is 0.1. So it's going to be 0.52 plus or minus 0.1, right? Which is going to be 0.42 to 0.62. Which is going to add 0.1 to it. Subtract 0.1 from 0.52 or add it to 0.52.
So where did you get 0.05?
0.05 was the standard error, right? This is P cap plus or minus 1.96 times the standard error. And I count for a proportion. This is the way I calculated the standard error. Okay, so can I say that Hillary Clinton's has more than 50% of the vote? No, I can't, right? Because my confidence interval includes values that are less than 50. It could very well, I'm 95% sure it's between these two numbers. I'm not even 100% sure of that, right? But that's where I would would expect, right? And in the long run, it doesn't matter anyway because the electrical college decided to vote anyway, so we don't have to worry about the compulsion. Yes.
Do you ever do the calculations for 99.5% rather than
Oh,
95?
I'm glad you brought that up. Okay, let's go back 1 second. Okay, somebody here, I won't mention his name, brought up the fact that, gee, if I look at that, if I look 5% area, it really comes up 1.64. Right? Okay, that 1.64 represents 5% at this end of the normal distribution and plus 1.64, 5% at this. So what percentage of the results are between those two? 5% here, 5% here, what's left in the middle? 90%. So if I were to take my X bar or my P cap, plus or minus, right, for a 95% confidence interval, I would use 1.96 times the standard error, right? Same thing here, 1.96 times the standard error. But if I wanted a 90% confidence interval, I would use 1.64 instead of 1.96. That would give me a 90% confidence interval. Which one of these two, if I take X bar plus or minus 1.96 times the standard error versus X bar plus or minus 1.64 times the standard error, which one, this is 99%, this is 95% confidence. This is 90% confidence. Which one of these is wider and which one's narrower? Is this one on the bottom wider or narrower? The interval. It's narrower. Why is it narrower? Because the 1.64 times the standard error is a smaller number that you're subtracting from each side, right? This is going to be a smaller number than this is, right? Because you're multiplying by 1.96 and 1.64 here. So this is going to be a smaller number. So I'm adding and subtracting a smaller number. So my interval here is going to be smaller than the interval here. So what does that tell you? If you make the interval narrower, you have less confidence that you caught the mean. Okay? What do you want? Anybody want to hazard a guess? If I want to have 99% confidence interval, a 99% confidence interval, what should I use instead of 1.96 or 1.64? Well, to figure that out, we go to our normal distribution and we figure out what z-score gives you 0.5% here and 0.5% here. And it turns out to be 2.58. Right? So you would use 2.58 instead of 1.96 or 1.64. So those numbers will become important to us as we go on because you might choose which one. But notice what's happening here. If you want a higher level of confidence, your confidence interval has to be wider. If you're willing to accept a lower level of confidence that you've captured the mean, you can afford a narrower confidence interval.
You should make the interval more narrow to get
a lower level of confidence, right? Because that's a smaller range. Okay, so I can tell by the packing up that like I've trained you to leave at the right time. Yes.